With this heat exchanger, there is no dead time. Now please increase the manipulated variable by 20% and investigate the step response. Please click the Simulate button. There shouldn't be any dead time, and yet there is a lag similar to dead time at the beginning of the change in control variable. This lag occurs not only due to the first-order lag that arises due to the transfer of heat, but also due to the first-order lag of the control valve or temperature sensor itself. So this sort of process response is called a higher-order lag. All right, let's calculate the time constant of this heat exchanger. First, find the point on the curve with the highest slope, and draw a tangent line at that point. Meanwhile, we'll call the time at which this tangent line crosses the time axis S1, and the time at which the tangent line crosses the settling value of the control variable S2. After doing that, we can see this has become similar to a first-order lag step response with dead time. The dead time and time constant that we calculate in this way, treating a higher-order lag step response as a first-order lag step response with a dead time, are called the equivalent dead time and equivalent time constant. All right, now please use the cross-shaped cursor to read from the graph how many seconds there are in the equivalent dead time and equivalent time constant. Then please select the appropriate number of seconds and drag it to the blank. That's right. The equivalent dead time is 4 seconds, and the equivalent time constant is 33 seconds. All right, now we're going to move the temperature sensor of the heat exchanger far away from the water outlet so that a pure dead time arises. Please increase the manipulated variable by 20% and investigate the step response. Please click the Simulate button. The equivalent dead time increased by the amount that the pure dead time increased. The equivalent dead time represents the sum of the pure dead time and the apparent dead time arising due to higher-order lag. Now, based on the tangent line that we just drew, let's use the cross-shaped cursor to find the equivalent dead time and equivalent time constant of the process. When you know the number of seconds in the respective times, please drag them to the blanks. That's right. The equivalent dead time is 14 seconds, and the equivalent time constant is 33 seconds. By the way, for this sort of higher-order lag as well, we can calculate the equivalent dead time and equivalent time constant based on the time when the control variable reaches 63% of the settling value in the same way as we did it for first-order lag. First, please use the cross-shaped cursor to find the time when the control variable is at 63%. Then select the number of seconds and drag it to the blank. That's right. It's about 39 seconds. From the 39-second point, S2, we draw a line perpendicular to the time axis and calculate the intersection point with the settling value of the control variable. Then we draw a straight line connecting that intersection point with point S1, where the control variable is considered to start changing when we treat this as a first-order lag. The amount of time from when the manipulated variable changed to point S1 is the equivalent dead time, and the amount of time from point S1 to point S2 is the equivalent time constant. All right, now please use the cross-shaped cursor to find the equivalent dead time and equivalent time constant, and drag the appropriate number of seconds for each to the respective blanks. That's right. The equivalent dead time is 14 seconds, and the equivalent time constant is 25 seconds. The equivalent time constant calculated by drawing a tangent line along the maximum slope direction in the graph is 33 seconds. The result was slightly different, but this method is convenient when the time constant of the process is long, and the maximum slope of the control variable is hard to ascertain from the graph.